right? In this video, we're going to prove how to find the sum of an arithmetic and a geometric series. And we're going to prove in general how we would find that. So let's start with a series. And we know that a series starts from a sequence, right? So we have a sequence of numbers as such. Now, just to review, we know how to write this as an explicit function and a recursive function. So take a second now, try that, maybe pause, and we'll come back. So our explicit function, we have a sub n equals our first term plus n minus 1. And in this case, we're adding 2 each time, so times 2. We'll distribute 2n minus 2. Oh, that is not an equal sign there. Should be a plus sign. -1 plus. And then we get our explicit equation, a sub n equals 2n minus 3. Our recursive function, a sub 1 equals -1. A sub n equals a sub n minus 1 plus 2. Good. So then, that's our sequence, right? Now, if we write this as a series, then we would say the sum, as n goes from 1 to 4, right? Because there are 4 terms. And we write our explicit formula there, so we get 2n minus 3. That would be our series. Our explicit we have, our recursive. So all of those things we've practiced finding, and now we want to figure out how to find the sum of any kind of series faster than just adding it. So if we take a look now at this, we notice that our -1 and our 1, those cancel, so 3 plus 5, we would get 8. But we're going to see if we can find that another way. So we'll come back to that. That's why I put a star. The star is not meaning multiply. The star just means we're going to come back to this. All right, so in general, we could also say that our sum is S sub n. So we're finding the sum of n is the number of terms that we're finding it for. So our sum, we take our first term, a sub 1, and we're going to add it to our second term. And our second term would have our a sub 1 plus the difference, right? And then we add it to our third term, so a sub 1 plus 2 differences. We're going to add this all the way until we add a sub n, whatever a sub n is. So this could be, we could have a series with 100 different digits, and this would qualify all of them. So that ... usually means like everything in between. So now, I want to think, well, what if we take this series and we just add it again? Or what if we add it, we look at it in reverse. So I'm going to look at S sub n. And if I start backwards, so I start with a sub n plus, and then I would add a sub n minus my difference. So notice how this top one, we started with, for instance, with our -1, right? And then -1 plus 2 gives us 1. Plus our difference, again, 2 differences from -1, we get 3. Now, this next one, we start with 5 in this example above, and we're going to take away our difference. So 5 minus 2, we'd get our 3 back. And we could keep going, right? We could say plus a sub n minus 2d plus ... all the way until we add a sub 1. So what these two are saying is exactly the same thing. It's just going in a different order. So S sub n at the top, that would be like our -1, 1, 3, 5, where this one would be 5, 3, 1, -1. Both of them are the same, right? Both of them would add up to equal 8, just writing it a different way. So let's add these. So these are equivalent. We certainly can add them together, right? So S sub n, we would end up with 2 S sub n's. And then we would get, if we look at our first 2 terms here, I'm going to switch back and forth. Our first 2 terms, if we add those, we would get a sub 1 plus a sub n. Then, if we add our second two terms here, so adding these together, notice that you would get a sub 1 plus d plus a sub n minus d. So the d's would cancel out, and we would end up with plus a sub 1 plus a sub n, right? Because the d's would cancel. Same thing for the next one. So you get plus a sub 1 plus a sub n plus dot 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 all the way until we get to a sub 1 plus a sub n. I just switched the order there because we know we have addition. It works under the commutative property, so I could switch those around. So how many times do I have a sub 1 plus a sub n? Well, it would appear that we have it n times, right? If we start at 1 and we keep going all the way to n, then we have it n times. So we have 2 s sub n equals n times a sub 1 plus a sub n. And now we want to get s sub n by itself. We would say s sub n equals n times a sub 1 plus a sub n all over 2. So this is the formula to add up an arithmetic series. So let's use this with our example above, okay? So I'm going to put a star here. So this is where we're going back to. So our n from the beginning, our n was 4, right? Our a sub 1 was negative 1, and our a sub 4 is 5. And we divide that by 2. So negative 1 plus 5 is 4. 4 times 4 is 16. 16 divided by 2, we get 8. And it checks. So we proved it mathematically. So in general, we have this formula, and then we just showed that it also works if we look at a specific example. So using this, notice where we found our n from, our a sub 1, our a sub n. All right, so that's for an arithmetic series. Now what about for a geometric series? We're going to prove that one also. So our proof for our geometric series. Now let's look at a geometric series here. So, geometric series. All right, first, let's just start with a sequence. So if I have 3, 6, 12, 24, 48. Then let's recall the things that we already know. We know our explicit form would be a sub n equals our starting number, which is 3, our common ratio, which in this case would be 2, to the n minus 1. Okay, our recursive form, a sub 1 equals 3, a sub n equals 2 times a sub n minus 1. Okay, so these, just a review for us, things that we should already have practiced. And then if we write this as a series, so a series, remember we're going to add it up. If you write this in summation notation, we have the sum, we use n equals 1, and we have 5 terms, so to 5, and we use our explicit formula, right? So 3 times 2 to the n minus 1. Good. Now if you go up here and you just add up all these terms, which you certainly could do, then we should get 93. Right? Because we get 10, we get 20, 30, 40, 50, 60, 70, 80, 90, and then we have the 3 at the end. Good. So we get 93 for our sum, and we have our answer here. Now, 93, we're going to come back to that again, and we're going to try to solve that with the formula that we get for geometric series in general. So we're going to prove this one. So same thing, we call it S sub n. And here's our proof. But in this time we start with a sub 1. So we're going to add a sub 1 times r. Okay? Plus a sub 1 times r squared. right? We're doing our ratio twice, plus a sub 1 times r cubed, plus dot dot dot, all the way to a sub 1 times r to the n minus 1. And that was our formula that we had, right? To the n minus 1. Then, I can have that same thing, but what I'm going to do with it is I'm going to multiply that whole set of values. I'm going to multiply it by r. So if I have r times s sub n, then I would have a sub 1 times r plus a sub 1 times r squared, right? I'm just multiplying it by r, plus a sub 1 times r cubed, plus a sub 1 times r to the 4, plus, and then I would have a sub 1 times r to the n minus 1, and I'd also have a sub 1 r to the n, right? So I showed this, oh, there's a plus here. I showed this, notice how this was n minus 1, so if I multiply it by r, at some point, if I have another r, I would get to r to the n, right? Because this was the one right before it, this is the last one. So what I'm going to do with these is I'm going to subtract them. I'm going to minus this whole line, and we'll see what we get. So we have, on the left side here, s of n minus r times s of n. And if we subtract the second line, then notice how we have a sub 1, so that stays, because we didn't move that at all, so a sub 1, and then a sub 1 times r minus a sub 1 times r. So these two, they cancel out, right, because we're subtracting. So we can keep going. These would cancel, these would cancel, this would cancel, there's another one in here somewhere. And then the term right before, those would cancel, and then we'd be left with a sub 1 times r to the n. So we would minus a sub 1 r to the n, and that's what it simplifies to. So now let's make it look a little neater. So we can factor out a couple things. I'm going to factor s sub n, 1 minus r, equals, and factor out a sub 1, 1 minus r to the n. And then I want to get s sub n by itself. So s sub n equals a sub 1 times 1 minus r to the n, divided by 1 minus r. And this is our formula to find the sum. So let's go back to where we found 93 before. So our a sub 1 was 3. We'll do 1 minus, our ratio was 2, so we'll do 2 to the 5th because our n was 5, divided by 1 minus 2. Alright, so we get 3 times 1 minus. Remember, we have to do the exponent first. So we get 1 minus 32 over negative 1. I'll keep going. So I got 3 times negative 31 over negative 1. So I have negative 93 over negative 1. The negative divided by a negative, we get 93. So this still works. This formula proved also, we could see that we get the same thing. So we'll practice using these formulas and trying to solve for different aspects of them. So this was if we were given a sub 1, r, and n, but sometimes we might be given s sub n or other parts that we'll have to solve for. So these proofs, we won't have to prove them again now that we've proven them. We'll get to use this equation for a geometric series and our other equation for an arithmetic series.